Hello, ladies and gentlemen. My name is Sakari Pallaspuro. I'm a senior research fellow at the University of Oulu, Finland. And today, with Martensitic Austenitic steels, their fracture toughness properties, and I want to address for this work in progress, especially Sebastian Lindqvist from VTT Technical Research Center of Finland, and Ann-Christin Hesse and Tamás Tóth from TU Braunschweig, who all did this welding part for this study, and also doctoral students from our unit who are working further. So, basic structure, introduction, then bit of these materials, and testing, and then to these results and conclusions, mostly for the picture. Okay, so in all our Finland, we have this Center for Advanced Steels Research, which is basically an umbrella for all the steels research happening in Finland, and also the largest steels research community in the Nordics. Here in the center of this is the Materials and Mechanical Engineering Unit, which divides into three different groups. Basically, microstructures and mechanisms for designing and developing these different processing routes, and then performance of steels for then industrial applicability, and then third, failure mechanisms to assess the end-of-life properties. So here in this research group, we have two main focus areas: fracture mechanisms, which I'm going to present today, and then hydrogen improvement and hydrogen steel interactions, where Dr. Renata Latypova is actually kept her presentation yesterday in this hydrogen embrittlement session. But yeah, those two teams. So with that, okay, first, sorry, I will give you a banana curve just for reference. So now we are talking about today on Martensitic Austenitic, so advanced high-strength steels with, let's say, yield strength, tensile strength starting from 1,000 and above. And what is important here with this is that, okay, if you don't do wonders, they will drop in tensile elongation. And here are also some of the results, what we have been putting there in a map as well. But of course, the session is structural integrity, so we need to look further. And applying this method, we know that when for these really high-strength steels, when we are able to iterate the processing correctly, we can expect to be able to extend this range of toughness properties as a function of yield strength when we have these optimized microstructures for these materials. So let's just look on this first. So we on the previous work that we did with the three different carbon contents from well, low carbon range 0.2 to higher medium carbon range 0.4. And what we can see with these alloys, that if you look on this impact toughness transition temperature T28, it can achieve really good properties, be it directly quenched or then also partitioned to increase the residual austenite when the carbon range is low. And then when you have like a medium range of carbon, it already matters a lot that what kind of processing you do for these steels. So can be fairly good when doing this partitioning treatment, and with just direct quenching, well, it will be completely brittle. And then if we go to up to 0.4 carbon range, then it doesn't matter much what you do, it will not be very tough. And further on to fracture toughness properties. So what we have been collecting from the literature to be able to see that, okay, where are the boundaries? Where can we go on these? So these are room temperature or ambient temperature testing for different combinations. So if we look on these BCC microstructures for these elastic stress intensity, you can expect a wide range of results, but okay, what would be, and then of course lower strength BCC, FCC structures are with the lower one, but those are unfortunately the typically reported values in the literature, but it doesn't make any sense if we are trying to do these elaborate materials to increase the work hardening rate, strain hardening, and overall deformability if you are measuring only elastic values. So jumping into these elastic plastic fracture toughness values, we also see that around the range of 100 megapascal square root meter, you can achieve with a wide range of yield strengths. This was actually our study on rapid tempering of these quench materials, that can you retain the strength and still recover deformability in the Martensitic microstructure with these optimized rapid treatments. So to the integrity part, so the assessment of these toughness properties. So in my presentation, the main assessment is in the master curve method and the ASTM E1921, and all of the standards and integrity procedures that follow these basic principles here. So for probability of failure, we know that it scales with the specimen thickness, and then this scaling factor. So for the median fracture toughness, it will historically follow this temperature dependence around this temperature level, where the specimens get thickness corrected stress intensity factor of 100 megapascal square root meter. So traditionally from pressure vessel steels, quench and tempered steels, and bionitic steels from the nuclear industry, as also shown in the previous presentation, that okay, there's the history, but it's applied to very many structural steels. So can we get something to that? So looking at the literature, many of these for very thin sheets for similar microstructures work with the work of fracture and then the K1C. But then looking a bit further, that can this low fracture toughness really be true despite this good tensile ductility and maybe even good impact toughness properties? So my open questions here for this presentation are that can we answer to the needs for low temperatures? Are they can they be tough still at well, let's say Nordic temperatures, for instance? It's already starts to be cold there. Despite here it's still quite warm. And could we get something out of these temperature correlations between fracture toughness and impact toughness that are employed to many different tables where you need to decide that what kind of steel range you can use? So let's proceed quickly. So three different groups of steel: 0.2 carbon, 0.3 carbon, and 0.4 carbon. And we did this in our laboratory hot rolling mill. So in short, we did hot rolling and quenching directly after the final rolling pass, and either we did direct quenching to the ambient water temperature, or then this partitioning with interrupted quenching temperature, with the idea that we can retain more austenite in the microstructure. And then how is it done, or what kind of morphology it is, will dictate completely the properties. So for these materials, we have a yield strength range from 900 to 1500 megapascals, tensile strengths from 1500 to 2500, rough around 10% of elongation, still quite moderate, well, sufficient to these strength levels. Hardness from a bit below 500 to 600, and yeah, here the retained austenite content from 0 to or a bit below the detection limit to 15. So we also did electron beam welding for these materials in Technical University of Braunschweig, and we can discuss these details later after this presentation. But then fracture toughness testing according to ESTM 1921 with 3-point bend test specimens to get these raw temperatures. So what do we get? First, to understand that these are lat martensitic microstructures with essentially film-like retained austenite. So we don't have like this duplex type of structure where we have big grains of BCC and FCC, but the FCC in these is laminated between the martensitic lats, at least for the range of 0.2 to 0.3 carbon steels, but already with 0.4 carbon alloys, we start to get also blocky morphology of retained austenite. So larger globular particles of high carbon metastable austenite that which will then under strain turn into very brittle martensite. So to start with this carbon range for these fracture toughness properties, what is the most curious thing here that if you do like ambient temperature testing, we start to drop out of this temperature dependence. So basically, the austenite there may not improve the properties to as high extent with the high local stress concentrations as hoped. But what we can get is very good low temperature toughness properties. So for instance, if we use this fracture toughness reference temperature T0, we see that it's well below 0 and even in the minus 50, minus 60 degree range for low carbon steels. But if we jump to 0.4 carbon, it's already, well, it's not there. They are not tough at all. And when we are looking a bit on how do these then deform, that on this direct and partition material, well, this was the case with interrupted testing. And well, we can see here on this individual case that it's on this stopped in the prior austenite grain boundary. But if we look a bit further, we see that there's still a high level of local deformation on the crack front and around the crack front. So still, despite these strength levels, we have some local deformability. And also, if we take just this direct quench version without retained austenite, or at least close to the detector level, there's still lots of local plasticity playing. But what is then limited is to that how high extent it can dissipate the stresses through the deformation here. So if we want to take a few short take-home messages, how much do I have time? Time is
1 minute.
1 minute. Okay, good. So basically, what do we want to know? That these high carbon, medium carbon materials are basically completely insensitive because of these blocky austenite there embrittling these materials. But then when we have like moderate carbon contents, we can still improve these properties as long as those are like laminar microstructures. And then I will apparently run a bit. So also for these electron beam welded materials, so environmental effects excluded, we see that properties are fairly in level with the hardness of the base material. So we achieved that there. So low mismatch, that's good. And there's also good level of impact toughness. But then when we are looking at the fracture toughness, that from this level of minus 30 degrees or minus 60 degrees Celsius, we still get to T0, well, sorry, provisional at T0 of around minus 40 degrees Celsius. But we are still working a bit more to truly explain these low deformation properties. But what is the challenge? If you want to employ then the structural integrity approaches, we see that at least these too widely exploited these 0T28 joule correlations between the impact toughness and fracture toughness break down when you start to introduce austenite into this matrix. So basically, we are here in the completely non-conservative side. And then when we are starting to look on these difference between these temperatures, we see that for BCC dominant materials, we have a good temperature correlation there with a wide range of yield stresses, but then when we put austenite there, it fails apart. So basically, the take-home message is that we need to establish, if we are going to use these for structural applications, I mean, not static, but mobile structures. We really need to establish how to assess these the fraction of the effect of austenite in these materials. But basically, with these laminar structures, you can achieve really good fracture toughness properties. But now I ran out of time, and sorry for that. And also for these electron beam validated values, despite the carbon equivalent is around the level of 0.7, they still are valuable, at least with these conditions. But the challenge is that then if you need to apply the post-weld heat treatment, it will actually ruin your properties that you achieved with these, well, at least the alloy design. So with that, I thank you, and maybe we discuss more then afterwards.